The next test I want to go over is called the ratio test on page 20. And this is probably one of the most important tests that you'll come across because we'll eventually be using it in the latter part of chapter 9. So if you could circle this and star this and just write down very important. Okay, so the ratio test states this. You have your given series and it has to be positive terms. And so if it's an alternating series, then you need to make sure that you take the absolute value. Okay, so you're going to be taking P equals and write out the limit of the next term. So it's U sub k plus 1 and divide that by the current term or the nth term or the kth term, which is U of k, and take k out to infinity. All right, so you're going to be creating this limit, and then the conclusion are three things. So if this limit is less than 1, then the series converges. If the limit p is greater than 1, or if p equals infinity, then the series diverges. In the case of p equaling 1, the series may converge or diverge, which means that it's inconclusive. So then that means that another test must be tried. So this is very similar to the geometric series test. Okay, so I'm going to write that over on this side. It's similar to geometric series. And in the geometric series, it states that the absolute value of the common ratio, if it is less than 1, then it converges. And then if it's greater than or equal to 1, then it diverges. So it's just a little bit different for this part C. All right, so here's the first example. Use a ratio test to determine whether the following series converges or diverges. So I write out my original statement with the limit. P is equal to the limit of U of k plus 1 over U of k as k goes out to infinity. So I put my, in place of the k here, I'll just say k plus 1 because that's the next term. So it'll be the limit of 1 over k plus 1 factorial all over, and then the term that's given, or the series that's given, is 1 over k factorial. So then simplify that, and I get the limit of k factorial over k plus 1 factorial as k goes to infinity. And then I'm going to rewrite the k plus 1 factorial in the denominator as k plus 1 times k factorial, and then up in the numerator is a k factorial. Right, so the k factorials cancel out, so I'm left with 1 over k plus 1, and then as I take k out to infinity, it equals 0, which is less than 1. So then by the rule that's stated up here, the series converges. So the ratio test is actually very good for series that have factorials in them. Okay, here's the next one. The series is k over 2 to the k, and I wrote out my general. P is equal to the limit of U of k plus 1 over U of k as k goes to infinity. And then I wrote out the k plus 1 term, which is k plus 1 over 2 to the k plus 1. Multiply that by the reciprocal. I just made it as a reciprocal right away. 2 to the k over k. And then I'm going to rewrite it. Remember that 2 to the k plus 1 is the same thing as 2 to the k times 2. So the 2 to the k and 2 to the k cancel out. So then I have a 1/2. I could just bring the 1/2 out in the front. And then k goes to infinity of k plus 1 over k. So this limit goes to 1, and then I multiply it by 1/2. So it's 1/2 as the p value, and that is less than 1. Therefore, the series converges. Okay, why don't you turn off the video, and I'd like you to try C and D on your own, and then come back and check your answers with me. All right, let's go over C. So in C, I wrote out the general, and then in place of your k, I'm putting in k plus 1. So it's k plus 1 raised to the k plus 1 over k plus 1 factorial. And then multiply that by the reciprocal, which was k factorial over k to the k. And then I just rearranged the terms in the numerator and the denominator so I could just cancel easily. So this k plus 1 to the k plus 1 is the same thing as k plus 1 to the k times a k plus 1. This k plus 1 factorial can be written as k plus 1 times k factorial, and then this k factorial will just stay as it is, and the k to the k will be just written as k to the k. Okay, lots of k's in this problem. All right, so then you get k factorial cancels out. K plus 1 cancels out with k plus 1, so then you're left with k plus 1 to the k over k to the k. All right, so then I simplify this, and I just rewrote it as a k power. And then I can also simplify inside the parentheses as k over k, which is 1, plus 1 over k raised to the k. Now you should recognize this as our Euler number of e. This is little e. So this right here is e, and that is greater than 1, 2.718. So this is about 2.718, which is clearly greater than 1, so this series diverges. All right, so this part right here, why don't you put it on your file folder and make sure that you have that one memorized. So this is definition of E, definition of little e, and you should memorize that. Okay, and here's the last example. No, actually we have two more examples. So here is our original, and then I'm taking the factorial. Now in this one, be careful that the 2k has the whole thing is with the factorial. So notice I put double parentheses around this. So it's 2 and then k plus 1, all of it is factorial. 4 raised to the k plus 1, and this is 4 to the k all over 2k factorial. Right, so then I simplify all of that, and I end up with 4k, and then this will be the same thing as 2k plus 2. Right, so it's 2k plus 2, 2k plus 1, and then I have a 2k. I forgot my factorial. All right, then the denominator can be written as 4 to the k times 4, and then you have your 2k factorial. So the 4 to the k cancels out, and the 2k factorial cancels out. And so then you're left with 1/4, and then the limit, and then what's left up in the numerator, and that goes to infinity. And so we're using that second case where p is equal to infinity, therefore the series diverges. Okay, there's one more example on page 21, so let's go through that one. So for this one, I work through this and I end up with 1 over 2 quantity k plus 1 minus 1 times 2k minus 1 all over 1. And so work out the algebra on that, and I end up with 2k minus 1 over 2k plus 1, which is equal to 1. So this is the inconclusive one. So by the ratio test, it's stating that it could be either converging or diverging. So you have to try another test, right? So I use the limit comparison test, the one that we did for the second one. And so I'm comparing it to the harmonic series of 1 over k. And so I take the a of k over b of k, and then I work this limit out, and I get that the limit is 1/2, which is finite and positive. Therefore, since 1 over k diverges, since it's harmonic, then the original one, a of k, diverges. You could also use the integral test or the comparison test on that problem.